Hey guys, my name is Poppy John. I'm going to be working on problem 3, condition B for questions 1 and 2. Hey guys, for this problem we have a woman doing a 30-degree squat. Both external forces are 300 newtons and 100 newtons going down, 0.1 meters anterior. Alright guys, so we're going to be solving problem B, which is a woman at a 300-degree squat. We have both our external forces, our body weight going down 300 newtons, and our plant weight also going down 100 newtons. Our plant weight and our body weight are both 0.1 meters away from our axis, which is going to be L4, this point right here. And our muscle force, the moment of our muscle force is 0.05, going perpendicular from our axis, which is L4. So to solve for muscle force, add up the external torques and divide by 0.05. So we have 300 newtons times 0.1, this is for our body weight, plus 100 newtons times 0.1, this is for our plant weight. When you plug that into your calculator, your answer should be 800 newtons. That's our muscle force. So we know that our body weight is 300 newtons and our plant weight is 100 newtons. You can add them up for a total of 400 newtons. That there is going to be our hypotenuse right here. Afterwards, you want to resolve for y. To do that, draw a line perpendicular to the lever arm. This is our y component. So we know it's a 30-degree squat, 30 degrees relative to this horizontal, making this 90 and this 60. So if we know that that's 60, we also know here is 60, and on the other side is 30. So to get our y, we need cosine, adjacent over hypotenuse. So our y equals cosine 30 degrees equals our y over 400. So bring the 400 over. And you should get 346.41. Now add both compressive forces together. Our muscle force, which is 400 newtons, plus our y, another compressive force, 346. And you should get 1,146.41.
Hi guys, my name is Amir Salsa Billy, and I'm going to be solving for problem 3, condition C.
Hey guys, it's Amir, I'm back again. We have this lady doing a 30-degree squat to pick up this plant off the ground without bending her knees. So right here, in this section, we have the L4 vertebrae, and it's at a 30 degrees angle to the horizontal, right? Then there's two different forces acting on it. The body weight and the plant. These are our external forces. Then we also have the muscle force right here. So let's first figure out the torque, the external torque. Since the plant and the body weight both have a moment arm of 0.2 meters, we can just multiply that by these values of 300 newtons plus 50. It's going to be 350 times 0.2 equals, let's throw in a calculator, equals 70. And now for the units, Nm, and now we can make the external torque equal to the internal torque. 70 will equal, we do not know the force for the muscle, but we know the moment arm is 0.05. x. X is going to be 70 divided by 0.05. This is the muscle force right here, 1400 newtons. So we found the value for the muscle force, which was 1400 newtons. And the good thing is, this force, as mentioned on the problem, is perpendicular to our L4 vertebrae surface. Therefore, all of the force is going to be a compressive force. But this one right here, which is a 350 newtons, the weight or the force for the plant and the body weight, it is not perpendicular. So we have to resolve this force. So let's make this right here. And this right here is going to be our compression force. There is our shearing force, but we only care about the compression force right here. So now we have to find the value for this angle. We know this is 30. This is 90. This right here is 60. So therefore, this right here too is going to be 30. So now we know this is 350 newtons. This is 30 degrees. Let's find the value for this. This is the adjacent side of a triangle, adjacent to the angle. This is the opposite. So adjacent, we have to use cosine. 350 times cosine of 30 equals 303.1. So this is the compression force for the external forces. It's going to be 303.1, but I'm just going to keep it right here for the significant digits, 303 newtons. Now, you have to find the total joint reaction forces, all the compressive forces together. The internal force for the muscles pulling this way, the external force is pulling this way. So both are pulling at it, and we're going to add those numbers together. And my pen slipped, it's a little butterfingers. Oh, now it's not working. So let's go back to my red pen. $1,400 plus 303. That's a huge number. 1703 newtons total compressive forces.
Hi class, my name is Jens Nicholas and I'll be doing problem 3, condition D.
All right, now for condition D, we have a woman doing a 60-degree squat and she's picking up a 50 Newton plant.
All right, so for condition D, we're gonna have her at a 60-degree squat. So from the horizontal here, she's gonna be at a 60-degree squat. So that's kind of the surface of her L4 vertebrae. And so what we have here is our force of the body weight and the plant weight. So for our body weight, we have 300 newtons, and our plant weight is going to be 50 newtons. And then, so we're going to be solving for that muscle force. And like we said, it's going to be perpendicular to the surface of the L4. And so to solve for the muscle force, what we have to do is make our internal torque equal our external torque. And so to get our external torque, we're going to take our 300 newtons times, and right here, so this is our moment arm for our body weight and our plant weight, which is 0.1 meters, and then we're going to add that together, so 50 newtons times 0.1 meters, and that's going to equal 35 Newton meters.
And so now that we have our external torque, we can get our internal torque, which is equal to our external torque divided by our muscle force moment arm, which is 0.05 meters. And that's going to equal 700 newtons. All right, now we want to calculate the total compression that's happening on our L4 surface here. And so for our muscle force, it's going to be aiming down at a perpendicular distance. So we know that all of the muscle force is going to be a compression force. And to get the compression force for our plant weight and our body weight, we're going to resolve it into an X and Y value. And so our lever arm is going to be in line with our L4 surface. And so we want to draw a perpendicular line here, which is going to be our Y, which is what we want to solve for. And then our X would go here. So this is our Y. And that is going to be, like we said, at a 90-degree distance. So if we look here, because this is a 60-degree angle and we have and that's perpendicular to our body weight and plant weight, we know that this is going to be 30 degrees. And so because of that, we also know that this is going to be 30 degrees, which ties into here. And because this is 90, this is going to be a 60-degree angle. And so that's going to be the angle that we're working with. All right, so to get the value for our Y, we're going to take our force that we have here. So we have 300 newtons plus 50 newtons. So we have 350 newtons going straight downwards. And now to solve for our Y, we're going to use the cosine of 60 degrees. And we're going to times that by our force here. So 350 newtons. And that's going to give us, so if we do 60 times 350, 175 newtons going in that direction. And so now we're going to want to add up both because they're both in the same direction going downwards, acting as a compressive force. So our total joint reactive force is going to be our original muscle force, so 700 newtons, plus the 175 newtons from our body weight and plant weight. And so then we're going to have 875 newtons of compression on the L4 axis.
Hi everyone, it's Amir again. So here we have all the values for the muscle forces, the back extensor. And these are the forces, the compressive forces. Hey guys, it's Amir again. So here we have conditions B, C, and D. These are the muscle forces for the back extensors. These are the total external components in terms of the compression forces, which is the body weight and the plant. And all of these are all compressive forces because the line of action of the force is perpendicular to the surface of the L4 vertebrae. So now let's add them up. 800 plus 346 is 1146 newtons. 1400 plus 303 is 1703 newtons. And 700 plus 175 is 875 newtons. So now we're going to rank these total compressive reaction forces from smallest to biggest. Smallest is D, 875 newtons. Then second is B, 1146 newtons. And the biggest is C, 1703 newtons.
All right, now we're going to look at some of the differences between the conditions, and we're going to see how that affects the overall compressive forces on the L4 joint. And so one of the main things we see is with an extended moment arm like we have in condition C, it's going to increase the overall amount of torque that's placed on the opposite side, so your muscle is going to have to work harder, which is going to increase the overall compressive load. And then the second main difference that we noticed was the angle in which which was applied on the load by the L4 vertebrae. And so we have a 60-degree angle here, which is going to angle your L4 vertebrae more in line with the shear forcing of the load versus its compressive load. So there's going to be an overall less compressive load the more angle you have compared to the other ones here, which is only 30 degrees. And so that's going to also increase your load.